Section 2.1 and 2.2, page 5. Now we're going to talk about applications of derivatives and specifically higher order derivatives. So think of a function as a position. It's telling you your position in time. So you plug in some sort of time x and you can know where you're at the end of that period of time. The derivative of that position is considered velocity. And think of velocity as telling you how fast you are going to get to that position and really what direction. Then it turns out we can take a derivative of a derivative, and this is referred to as the second derivative, and its information is about acceleration, how fast your velocity is changing over time. So let's look at example 6 below. We have three functions. One represents the position of an ant as it's moving along a sidewalk. Another function represents the velocity, which is how fast and which direction the ant is moving. And the final function is acceleration. And acceleration is telling us how the velocity is changing over time. So in this particular case, this red graph, option C from below, is the position of the ant. At 0 moments in time, its y height, its distance is 0 feet or inches or centimeters, whatever measurement we're using for this ant. But as the time increases, the ant seems to be moving, although there's that flat section, so we'll talk about that. Graph B, which I write in green, closest to this color I could get, is telling us how fast the ant is moving. It kind of sped up and then slowed down, but notice it continued to move in a forward direction. Whereas graph A, the derivative of graph B, is the acceleration, which is how that velocity is changing. So even though the ant, looks like it sped up and slowed down, it actually was going super fast and then almost dropped and maybe stood still for a while and then continued to move along. And so we've got information about all the components of the ant. And let's talk about the units on all of these derivatives. So the function of the ant was maybe measured in centimeter, inches, whatever the case may be. But what about a derivative? A derivative's units are the change in the function itself, the y value, the f of x value, whatever the output is measured, as dependent upon the change on the input, the x value, or whatever that's measured as. So example 7 says, let g of t be the distance a car has traveled in miles after t hours. What does g prime of 1 represent, and what are the units? So let's start with the units. The units are the output. The output is g, and it tells us g is telling us the distance of the car, and the input is t, and t is the time. But you want to be careful. How are distance and time measured? We were told that g is distance, but specifically it's distance measured in miles, not inches or centimeters like you would measure for an ant. And how is time measured? It's measured in hours. So when we talk about the velocity of the car, it's going to be in terms of miles per hour. How fast was the car driving and in which direction is its velocity? So with g prime being the notation for a derivative, and we know derivative is velocity, the question was, what does it represent? G prime represents velocity. What are the units? They are in miles per hour. And because our input is t equals 1, that it's in 1 hour. Here's another example to help better understand that. Example 8, you drop a ball from a balcony. The position, we'll just stick with position, that the ball has traveled after t seconds is given by this particular function, and you're asked to find the velocity of the ball after 2 seconds. So not where is it relative to where it's been dropped, but basically what is the speed, if you want to use that phrase. How fast is the ball moving? So our goal is to find velocity, which is the derivative, and specifically with an input of 2. So since t is 2, we're going to go ahead and use the previously shared equation 2.1a that says if you want to take the derivative of something at a specific value a, then you can let the variable, in our case it's t, not x, approach that value where we're going to take the function in its original format and we're going to subtract it from that function where a 2 is plugged into the function divided by the input minus whatever our specific value is, and that's what we're taking the limit of. I can't plug t in as 2 here because it would end up giving me a 0 denominator. There's really no math to clean up in the first term, and even though I can square the 2 in the second term to get a 4, and it's tempting to multiply 4 with 4.9, remember that our goal is to eliminate the t minus 2 binomial in the denominator. And so by multiplying this, it's going to be a lot harder. Whereas if you notice, I have a black 4.9 in front of each term. I can factor that 4.9 out to just leave me with the t squared minus 4t, because this is a binomial that is of the form a plus b, a minus b, so that when I factor this out, I then do have something that cancels with the denominator to give me a limit where I don't have t equaling 2 causing a denominator of 0, so therefore I can go ahead and plug that t equals 2 into my equation and get my derivative, which in this case is the velocity. In terms of units, we're looking at the output, which is F, and F is measured in feet, and the input t, which because t is referenced as 2 seconds, it's in seconds. So this ball dropped from the balcony, traveling at a position of 4.9 t squared feet, will be at 2 seconds later 19.6 feet per second as a velocity.